So let's jump right in with the ultimate engineering mystery. It's a question that literally starts wars in engineering departments. Should you ground a cable shield at one end or at both ends? Here's the catch. Grounding a shield at one end solves a massive system crashing problem, but doing so instantly creates a deadly vulnerability to a completely different type of noise. It's exactly like sealing a high-pressure water pipe to stop a leak in one room, only to have the pressure blow out a valve on the totally opposite side of the building.
The simple answer is that it depends. But hey, we aren't going to just leave it at it depends. We're going to strictly define the exact variables it depends on. We're going to look at the frequency thresholds, the actual mathematical formulas, and the physical reality of what happens when you make the wrong choice.
Let's kick things off with Section 1, Core Concept, Capacitive Shielding.
To really understand how shielding happens, we need to look past the surface of the physical cable and zoom straight inside the material at the atomic level. We have to visualize capacitive coupling. Those electric field lines act like invisible springs directly connecting conductor 1 to conductor 2. Picture a tightly packed crowd in a stadium. When one section suddenly shifts, the physical pressure forces the next section to shift as well, right? That's exactly how a displacement current is created by atomic polarization. But once we wrap conductor 2 in a grounded shield, that shield physically intercepts those invisible springs. It aggressively shunts that shifting crowd of energy straight to ground before it can ever touch our sensitive inner wire.
Moving right along to Section 2, the shielding math breakdown. Okay, let's actually dive into the math to prove exactly why adding a properly grounded shield dramatically reduces that parasitic mutual capacitance. We aren't just guessing here, the physics give us a strict rule book. For shielded cable, our equivalent circuit relies on one very specific condition. The resistance to ground, R, must be vastly smaller than the total capacitive reactance of the system. Mathematically, R must be much, much less than 1 divided by the complex frequency expression J omega times the sum of C12 plus C2G plus C2S. Think of resistance R as a wide-open multi-lane highway for the current, while the capacitive reactance is a narrow, heavily congested toll booth. Because that highway is so much easier for the current to travel down, this complex condition simplifies beautifully to Vn equals J omega times R times C12 times V1.
Well, let's break down what this simplified expression physically tells us about the materials we're using. Vn is our noise voltage. That's the enemy we're trying to defeat. It is directly equal to J omega, which is the angular frequency. Physically, this means the faster your signal changes, the worse the noise gets. Next is R, our terminating resistance. That gets multiplied by C12, which is the mutual capacitance between the source and any unshielded portions of our wire. And finally, V1, the source noise voltage. Here is the absolutely crucial takeaway. By adding the shield, we've drastically reduced C12 to near zero. The only mutual capacitance left is whatever manages to leak through the tiny microscopic holes in the shield braid. If C12 drops to near zero, the math dictates your noise voltage Vn drops to near zero. The math literally proves the magic.
Now for Section 3, solving practical grounding problems.
So, applying this to the real world, where exactly do we terminate the shield? We know the shield kills mutual capacitance, but only if it's properly grounded. If you leave it entirely disconnected, it basically becomes an antenna, sucking noise right back into your signal wire. And this brings us to the great frequency divide. For low-frequency signals, under roughly 100 kilohertz, we use a single-point ground. But for high-frequency signals, over 100 kilohertz, we absolutely must use a multi-point ground, connecting both ends. The physics strictly demand two completely different approaches based on frequency.
Let's look at low frequencies. Here, our primary enemy is the 50 or 60 hertz power grid. If we grounded our shield at both ends across a large building, any tiny difference in the Earth's voltage potential between those 2 points would drive a massive 60 hertz current right through our shield. This is what we call a ground loop. Think of it like a bathtub with 2 drains set at slightly different heights. The water is just going to constantly slosh back and forth between them. By grounding the shield at only one end, preferably at the source, we physically plug one of those drains. The sloshing completely stops. The current cannot flow, and the power frequency noise is eliminated. Which brings us to a major trap in Section 4, the high-frequency stray gotcha. Right around that 100 kilohertz mark, the physics flip, and engineers fall into a dangerous mathematical trap. What worked perfectly for a low-frequency audio amplifier will completely destroy the integrity of high-speed digital communications. Why? At high frequencies, the electrical signal is moving so fast, it actually doesn't even need a physical copper wire to travel. It uses the ambient stray capacitance of the environment like an invisible leaky pipe to jump from the open end of your shield straight to the ground plane. You thought you left the shield ungrounded to prevent a loop,
But high-frequency physics just bypasses the open circuit and completes the loop anyway. Plus, as your cable length approaches 1/4 of the signal's wavelength, that open-ended shield transforms into a perfectly tuned radio antenna, dragging massive amounts of RF interference directly into your sensitive system. We need to pause here for a strict real-world engineering reality check. If you want to calculate the exact high-frequency noise voltage for your specific ungrounded shield, you're going to find out real quick that a textbook cannot give you the numbers. Ott's formulas are perfectly derived, for sure, but he cannot provide the precise mutual capacitance, C12, or the source voltage, V1, for your specific installation. Straight capacitance depends entirely on how close your cable is routed to a metal chassis, exactly how it's bent, and even the local humidity. To actually complete this math on site, you can't just guess. You must use an LCR meter to explicitly field measure these parameters.
So what do we do when things get complicated? Section 5. The hybrid and double shield solutions.
What happens when reality gets messy and your signal contains both low-frequency slosh and high-frequency digital noise at the exact same time, like in modern video broadcasting equipment? A single-point ground fails. A multi-point ground fails. The solution here is pure engineering ingenuity, an XLR connector utilizing a hybrid ground. By tying the cable shield to the connector shell through a ring of tiny surface mount capacitors, we exploit capacitive reactance. At low 60 Hz frequencies, a capacitor acts like a solid brick wall, a high-impedance open circuit that completely blocks the low-frequency ground loop slosh. But at high megahertz frequencies, that same capacitor acts like a wide-open door, a low-impedance short circuit that safely drains RF noise directly to the chassis. By paralleling multiple capacitors, we drop the stray inductance, creating a highly effective hybrid shield termination. Alternatively, if you just don't want to rely on hybrid capacitors, you can solve the physics physically by using a double-shielded or triaxial cable. This completely isolates the two problems. The outer shield is grounded at both ends to act as a Faraday cage, killing high-frequency RF and magnetic fields. Meanwhile, the inner shield is kept completely electrically isolated from the outer one, and we ground it at only one end. This perfectly protects our sensitive internal conductor from low-frequency capacitive coupling without creating a ground loop. Two shields, two different frequency targets. Beautiful, right?
Let's wrap this up with Section 6. Essential shielding takeaways.
Let's lock in the physics with a rapid-fire recap of the fundamental rules you need to pass your EMC compliance tests. Memorize this cheat sheet. For low frequency, anything under 100 kHz, use a single-point ground to stop the bathtub slosh and prevent 60 Hz power ground loops. For high frequency, over 100 kHz, use a multi-point ground. Ground both ends to cap the invisible leaky pipes of stray capacitance and utilize the skin effect. And for wideband signals that do both, rely on mixed terminations like hybrid capacitor grounds or double isolated shields.
By respecting the strict mathematical realities of capacitance and frequency, you turn the black magic of EMC into predictable, solid engineering. If you found this breakdown valuable, hit subscribe for more strictly factual deep dive EMC and automotive communication protocol survival guides. But before you go, think about your current circuit designs. Are you relying on a single point ground out of habit, or because the math actually supports it? Keep measuring, keep calculating, and I'll see you in the next explainer.